Hey y'all, this lesson is on hypothesis testing for one population mean when the population standard deviation is known. That's a lot of words, but basically we're using the p-value approach or the critical value approach to test a value to determine if the population mean is plausible or not. So we've done all these things to estimate the population mean, or maybe a company has claimed a population mean. And then we're using real statistics, real samples, a sampling distribution of the sample means to figure out if we can reject or not reject the fact of the value of the population mean. Before we get into hypothesis testing, let's first review just a little bit of the p-value and the critical value approaches. Before we get into that, I do want to remind you that when we talk about a z-score, we use this formula in the box here. I think in my last video, I wrote the general form or the general formula for z-score. So we know that to find the z-score, we have to do x bar minus the population mean over the standard deviation. But we're basing this off of a sampling distribution. So now our standard deviation depends on our sample size. So you would further that. This was kind of a general form. And this is what we're using for hypothesis testing. So we found that in the video with the sampling distribution for the sample means that the standard deviation changed based on sample size, and we found the formula for that was this here. So that's what we'll be using for hypothesis testing. And we use this z-score to standardize our variable so that we can compare it to a standard normal curve, which helps us use, z-tables. Our calculator doesn't necessarily need a standardized variable, but if you do use the standardized variable, then it's easier to type in basically. But so the critical value approach was we basically used our data to calculate a z-score of our test statistic, so some value that we're testing, and compare it to the z-score associated with our significance level alpha. And we decided the z-score associated with alpha, that's our critical value, by deciding whether it was two-tailed, right-tailed, or left-tailed. And so that kind of showed us like where the rejection region was. And that rejection region decided our critical value. And I kind of referred to it as a cutoff point. So our critical value provides a cutoff point. And if our test statistic is past our cutoff point, then that puts us in the rejection region. So for a left-tailed test, we have our standard normal curve, roughly, that's terrible, but and then we had, alpha might be 5%, and 5% had a critical value, I can't remember, I think it's 1.64. Let me check before I go spouting stuff off. Yeah, negative 1.64. And then if our test statistic, so the value that we're testing from our data fell in this region, this was the rejection region. So if it went past that critical value. And then the p-value approach talks more about, is referring more to the area. So alpha is an area, and if we use our test statistic to find the area for that test statistic, if the area was in the rejection zone, then we reject it. So the p-value, you find the p-value or the area. P-value is a probability, and probability is a percentage, which is an area, for the test statistic and compare to alpha. We found that if P was less than alpha, that we reject the null. So if P, the probability of our test statistic was smaller than our significance level, it put it in that rejection zone. And I think I drew a picture here. We were able to see with the colors, like on this one, our p-value was 0.07, which put it inside, securely inside our rejection zone. So that's what we're comparing. And you don't have to do both of these approaches for hypothesis testing. You can pick one. So for the notes purposes, I show both, just in case you pick one or the other. That way you can see both. But moving forward, as you do, you know, practice problems or homework or tests or whatever, or your own study, you don't have to do both. You could do both to check your answer, but you just pick one. So I have an example here. We're going to perform a hypothesis test at the 5% significance level. So this provides, that is our alpha. Our alpha is 5%, which is 0.05. And that's going to help us make our decision because it's going to provide that cutoff point. And then pay attention here. It does give us the sample mean. It gives us the sample size, the population standard deviation. In my next video, we won't know that, which oftentimes is true. We won't know the population standard deviation, and we have a different method for that. But for this case, in textbook world, yay, we get to just know it. And then we have the null hypothesis right here, and all our alternative hypothesis. Now this is important because this tells you the tail of our hypothesis test. So we're testing less than, which is left-tailed. So if I were to draw a little sketch of that, my 0.05 would be on the left because it's less than the mean. So restate the null and the alternative hypothesis. Our null hypothesis is that it equals the population mean. And our alternative hypothesis is that it's less than. And that sets up our test. And the significance level is 5%. So that means that alpha equals 0.05. In decimal form, 5% is 0.05. Now, we're going to compute the value of our test statistic, which is based on our sample mean and our sample size. And this test statistic is going to give us that information we need to test whether the population mean is plausible or not. So we have 20 minus 22 over 4 divided by square root n. And then if you type that in your calculator, actually I have a calculator, I forgot. I invested in this $5 calculator. 20 minus 22 divided by 4 over square root n. I think I typed it in parentheses for the numerator, parentheses for the denominator. It should be good. Uh-oh, it's mad at me. Oh, I see. My other parentheses is inside the square root, and it doesn't like that. So let's see if I can fix that. Still an error? Hold on. Okay, I had an issue with my parentheses. When I typed in the square root, I put a parentheses inside the square root, so that was the problem. So our test statistic is negative 2.83 if I were to round it. So I'm going to go back here, and that is negative 2.83. I'm actually going to change this equal to an approximate because I rounded it. Nitpicky, but it's been drilled into me. So that is the value that the z-score that we're testing. And that's going to play directly into both approaches. So I'm going to do both of these by hand. You can do this on the calculator, which I will show you, and you will enjoy it, but I want to show you by hand before you learn that part. So the critical value approach, we have our test statistic, but I need to know the cutoff point. And the cutoff point is based on the alpha of 0.05. Now, alpha is an area, so I need to know the z-score associated with that area. And we're looking for, in this case, the area to the left of 0.05. So if you have a z-table, you can get your tables, go look at the areas, that'll be the inside of the table, 0.05, and then figure out the z-score associated with it, and that's the z-score. If you're using your calculator to find the z-score, then I'll show you that. I am going to use inverse norm because I have the area. So I need the inverse of the area. I need the z-score. And I can type in 0.05 because that's the area to the left. And I don't need to put 0 and 1 because it's going to assume that it's standardized. And we get negative 1.645-ish. Whoops. So if I were to draw a picture of this, which I don't have a lot of room for, but I can do it over here. Then here's 0, 1, 2. Negative 1.64 is about here. And that's the z-score associated with my alpha, my area. And then my test statistic is over here-ish, I'm estimating. So that puts it securely in the rejection region. So I'm going to tentatively say that we're going to reject, but I'm going to do the p-value approach also just to kind of show both. For the p-value, we are looking for the area to the left of our test statistic. So you can use your z-tables to find that area associated with that z-score, or you can use your calculator and do normal CDF. When you type in normal CDF, you have to tell the calculator what your region is. And we know, since it's a left-tailed test, that our region for our area we're looking for is from negative infinity to this test statistic. So I'm going to go to my calculator. I need normal CDF. On your calculator, you do second vars normal CDF. Mine, this calculator is on my iPad, and it just has my most recent things that I've typed in, so I just tapped on it. Makes it really easy. I'm going from negative infinity to negative 2.83. And this is standardized, so I don't need to put in the mean and the standard deviation. It assumes 0 and 1. And we get 0.0023. So that is, whoops, about 0.0023. And our alpha level is 0.05. So if I were to draw a picture of that, it's left-tailed with alpha of 0.05, and then 0.0023 would be an area really small. It's hard to see that. Make it blue. Over here. So since P is less than alpha, it puts it in the rejection region. Remember that P is the probability of getting that value, the mean of 20, assuming that the null is true. So the probability of getting a mean of 20 is 0.002, which is 0.2%, assuming that the null is true. So that's a really small percentage, which puts it in the rejection region. So we can say that we reject the null hypothesis because our probability of our test statistic is so small. So we can, to interpret that, you say at the 5% significance level, the data does provide sufficient evidence to reject the null hypothesis in favor of the alternative hypothesis. Remember from one of my previous videos, we never, ever, 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 ever accept. We can simply reject or not reject. So we're basically just testing plausibility, whether this can be true or not. And based on our probability for this one, we're saying we're going to reject this population mean. Okay, next one. I did mention that you can use your calculator. So this is the same exact problem. And I'm going to show you how to use your calculator instead of doing it by hand. Now, doing it by hand is a great practice so that you are seeing where these values come from and why we're doing what we're doing. But in the world of statistics, when you have really, really large data sets, you don't want to be doing them by hand because there's a lot more possibility for error in that. So it's good to learn to do it by hand so that you understand it, but then when you're actually doing it, I would recommend doing it by calculator or software. There's lots of software. So on the left of this table here, I have these steps for the finding the values we need. And we're using a z-test. So we use a z-test because we're finding z-scores because we know the population standard deviation. So you're going to see some different options there when you go to stat and then over to test. You're going to see some different options. You're going to see z-test and t-test. In this case, we're using a z-test because we know the standard deviation. So your calculator might look a little bit different than mine. You know, I use this one by hand, but since I'm trying to show it in the video, it's supposed to be pretty similar. This is a TI-84 for an iPad, and it was only $5. So if you have an iPad, you might look into it. It has pretty much all the same stuff that this has. I did find it does not have the normal probability plot. I couldn't get it to do it. So there's a few things it doesn't have, but for $5, it's pretty nice. So I'm going to go to stat. On mine, it is the first one, or I went over to test, sorry. And then on mine, it is the first option. I think on this calculator, over to test. Yep, first option. And it's going to ask you to input some information. So you can see at the top, it says data or stats. And I am putting in stats because that's what was given to me. So the null hypothesis was that the mean was 22. The standard deviation is 4. The value we're given for the sample mean was 20. And our, what do you call it? Sorry, words. Sample size was 32. And then down on the next, you're going to choose your test. Are we testing not equal to, less than, or greater than? This one was a less than, so I'm going to select that and then calculate. And you'll see here in the home screen that it gives us everything we need. Look at that. It gives us our test statistic, it gives us our p-value, and it shows a summary of some of the other information. So without doing it by hand and allowing for that error when you do it by hand, we get the values we need. Now, based on those values, you have to know how to make a decision. So the calculator doesn't make a decision for you as to whether to reject or not. So you have to know how to understand statistics so you can make these decisions and, you know, analyze what's happening. So we got a z-score of negative 2.83, a p-value of 0.0023, x bar was 20, n was 32. And our alpha level was 0.05. So let's pretend like we didn't do the problem on the previous page. Let's pretend like we just used our calculator and this is what we are finding. This is the reason I stated in one of my previous videos that I prefer the p-value, because we know the significance level and we're given the p-value from the calculator, and boom, you can compare it right there. If p is less than alpha, you reject. And I feel like it's faster. Now, if you like the critical value approach, then you'll have to take it one step further and find the critical value for this alpha level. And since it's left-tailed, whoops, then you do inverse norm, it's left-tailed, and you find that critical value, and then you can compare that way. So that's why I like the p-value approach. I feel like it's a little more direct, especially using the software that we use. So at the 5% level, we reject the null, so the data, does, I always get confused on the wording there, does provide sufficient evidence to reject the null in favor of the alternative. So that's calculator. Same exact problem done with a calculator, a little bit faster, a little more accurate. Go ahead and try the next one. You will be doing it by hand first, and you can use which test you want to use or which approach you want to use. If you want to use critical value or p-value, it does not matter. Do it by hand, and then I want you to check your answer by calculator just to make sure. So go ahead and pause it. You have the information in the top of the table. Go ahead and pause it and then try it and come back and check your work. So I did, on the left by hand, I did the critical value approach. And then on the right, I did the p-value approach. So you could kind of see both. For the left, the test statistic is about 1.22. And then since I used the critical value approach, I found the z-score associated with alpha of 5%. Now, keep in mind that this is a two-tailed test. So since it's a two-tailed test, we are splitting up the 5% into 2.5% and 2.5%. So when you go find your z-score for this alpha, you actually need to find alpha over 2 because we're splitting it in half. So our alpha in this case is actually 0.025. And you can find the z-score for either side, and it's symmetric. I found the right side, but it doesn't matter. And our test statistic is 1.22, and then our cutoff point is 1.96. So when we draw a little sketch of this, our test statistic is not inside our rejection region. It's in our non-rejection region, which means that we do not reject the null hypothesis. And then for the calculator one, I did the p-value approach. And we get a p-value of 0.22. And remember that this is a probability. So assuming that the null hypothesis is true, the probability of getting this test statistic is 22%, which is pretty high. Since p is not less than alpha, we do not reject the null. So it's outside of our rejection region. So if we were to draw it on this one, we would still have a two-tailed test with alpha as 0.025. And then our p-value is way outside our rejection. So we this was 5%, hopefully. Yeah. At the 5% significance level, the data does not provide sufficient evidence to reject the null hypothesis in favor of the alternative hypothesis. Pretty cool, right? Okay, this is the last example for this video, and I want you to either do it by hand or by calculator or both, whatever you prefer, but this is just a practice problem. So read this problem. Oops, let me zoom out a little bit more. And go ahead and try it, and then come back and check your work. Okay, I'm going to walk this one through with you. The null hypothesis, so it doesn't explicitly state that in the problem, but it does say we want to see if the mean age of diagnosis of all people with early onset dementia is less than 55 years old. So we know that 55 is the value that we're testing. And we want to see if it's less than 55. So our null hypothesis is that it is equal to 55. And our alternative hypothesis, the one that we're trying to see is, a possibility or not, is less than 55, which makes it a left-tailed test. And our tail is 1%. So that's an alpha of 0.01. And then we are testing a sample mean of 52.5, population mean of 55, standard deviation of 6.8, and we don't have N. Hold on. Very sorry about that. It's a little typo. N is 21. So you would not have been able to finish this problem without knowing that. If you want to pause it and finish it now and then check your work, then that's fine. Very sorry. So we're going to go ahead and find this. Whoops. Test statistic 52.5 minus 55 over 6.8 divided by square root 21. Hopefully I typed that in correctly, is about negative 1.68. And you'll notice that for the test statistic, we use Z sub X bar because we're testing this sample mean. And then I went ahead and did p-value. If you did critical value, that's okay. I'll show that also. But the p-value of this test statistic, let me use the calculator here. So we are saying our population mean is 55. Our standard deviation is 6.8. Darn it, we're doing stats. Forgot to select stats. Our sample mean is 52.5 and our sample size is 21. And then this, we are testing less than, I believe. Calculate. So there's our test statistic, there's our p-value, 0.046. Uh-oh. And our alpha level is 0.01. So you can make a decision at this point based on the p-value. Is p less than alpha? No. So at the 1% significance level, it does not provide enough evidence to reject. If you had done the critical value approach, then you should get z-score, the cutoff point of negative 2.33, which still negative 1.68 is outside of that rejection region, so you get the same conclusion that the data does not provide sufficient evidence to reject the null in favor of the alternative. So that is all for this lesson. I hope you enjoyed it. If you have any questions, please let me know and I would be happy to help.